Okay. Thank you, John. Thank you, the organizer, for organizing this program here in Cambridge and for letting me speak about this. So, as you've seen from the title, I will give an overview on recent advances in the control of continuous variables and quantum continuous variables. And in particular, this is the outline. I will start with a really brief introduction about continuous variable quantum systems, and in particular on Gaussian states and operation. I will basically repeat a lot of things that Alessio has already introduced in the talk last week. And then I will move to some results. The first one will be about open loop controllability of continuous variable systems, and I will show you how we have been able to generalize controllability criteria for Gaussian operations. And then I will move to closed loop control, so feedback control, and I will start talking about continuous measurement and feedback, and I will show some bounds on the squeezing and the entanglement you may achieve in this setup, and I will apply this to a few examples. In particular, we'll talk about the case of bosonic fields in a thermal bath, which, as we will see, there are a few things that we have to worry about. And then I will change a bit topic. I will still talk about feedback control, but now with continuous measurement. And the idea is to present a protocol where we have been able to generate squeezing in hybrid mechanical systems, and I will define this later. So I will start with the first part of the talk. So quantum continuous variables. These have been introduced by Alessio, and so basically we consider n bosonic fields, so described by canonical operators X and P, so they all satisfy the canonical commutation relations. They are really important in physics as they describe a lot of things, so the electromagnetic field, so the quantum light, but they describe, of course, mechanical oscillators, collective spins, and so on. Of course, you have the problem that the quantum state belong to an infinite dimensional Hilbert space, and so to get around this, so what usually people do is to restrict themselves to simple cases, and in particular, one may restrict to Gaussian states. So what are Gaussian states? Can be defined rigorously, both from a physical and a mathematical point of view, are all the only ground and thermal state of linear and quadratic Hamiltonians, if you add also that are bounded from below. And so if you have this kind of Hamiltonian, where this vector R is the one I introduced here, then if you consider any Gaussian state correspond to a thermal state of this Hamiltonian. And the good thing is that they're theoretically treatable, and we will see later why. Probably you already know all of this. And they're also relevant for applications because basically not all, but most of the states we can produce we can produce in the lab without many difficulties are Gaussian. Of course, coherent states are Gaussian, thermal states are Gaussian, but also squeeze states, which are non-classical, are Gaussian. So this is a good side of Gaussian state. And so here I will reproduce also, again, what Alessio did last week. I will be very fast. So on the left, we have what we have we have standard quantum mechanics, so we have the object we are used to. And on the right, we have the so-called Gaussian wall. So for every object on the left, we will correspond an object on the right column. So quantum state in quantum mechanics are described by operators in the Hilbert space, so operator rho. And for Gaussian states, you can describe a Gaussian quantum state just by considering their first moment vector R and the covariance matrix sigma, which is here defined. So then a good quantum state is a trace one operator, which is positive. Then you have also the canonical commutational relation for X and P. And this can be translated in the Robertson-Schrödinger relation, which involves the covariance matrix here. And the point here is that for every Gaussian state is described, correspond to a covariance matrix sigma, if and only if this is satisfied. So for any sigma satisfying this, you can find a Gaussian state. And for any Gaussian state, you obtain this relation. Measurements are described by P of M, so that they satisfy the completeness relation. And Then there are many ways to define Gaussian PRVMs, and one thing you can ask for is that the statistic will, for Gaussian input state, the statistic will be Gaussian, and the output state of the conditional state will be Gaussian. And so it's still an open question, but I think that most of this, basically this PRVM are what we call general dyne detections. We will speak about this later, but they include homodynes, so basically projection on the quadrature operator X, so an heterodyne correspond to projection on coherent states. The dynamics in quantum mechanics is described by a Hamiltonian operator H, and if you want to keep the dynamics Gaussian, then you have to restrict to quadratic, linear and quadratic Hamiltonian, so everything is described by linear drive D and the Hamiltonian matrix H. This will correspond to a unitary group here, so to unitary operation forms a unitary group, and in the Gaussian case, this corresponds to the symplectic group. So, and the evolution in terms of the covariance matrix is just that sigma goes into S sigma S transpose, and this S belongs to the symplectic group. Then you can consider also open quantum system, and if you have a Markovian evolution, then usually you can write this evolution in terms of a master equation in a Lindblad form, and in terms of the covariance matrix, they correspond to this matrix differential equation, and so everything is described by two matrices, A and D, so this is usually called drift matrix, and this is the diffusion matrix. So this is, one more thing about Gaussian states is that interesting features like squeezing and entanglement are all well defined and understood for Gaussian states. Squeezing is quite natural because basically corresponds to say that the smallest eigenvalue of the covariance matrix is smaller than 1. So below the short noise, this basically corresponds to saying that there is a quadrature in phase space such that the fluctuation are below the short noise. And also entanglement, you have a necessary sufficient condition in terms of this quantity, which is the smallest symplectic eigenvalue of the partially transposed state. You can easily calculate it from the covariance matrix, and you can say that the state is entangled, or and also quantify it. So now we can move to the results, so something probably more interesting. And so about open loop controllability of continuous variable system, this is something I've done in collaboration with Alessio and Daniel, who are here, and Myung-Sik Kim at Imperial College. So what I mean with controllability here, in open loop control, the situation is that is the following. You have an Hamiltonian operator H, which is divided in two parts. You have an operator H naught plus other control operators, control Hamiltonians Hj, that can basically switch on and off by means of this time-dependent function Gj. So, and we say that the Hamiltonian system is controllable if we can implement any unitary operation on the system by controlling this function, which usually can also consider just stepwise function. So you can, it really corresponds to switching on and off this controlling Hamiltonians. And the controllability is well understood for unitary compact groups. So when you have a finite dimensional system, and there is this well-known rank criterion that says that the Hamiltonian system on a finite dimensional space is controllable if and only if the operators Hj, where I consider also H naught in this set, form a set of generators of the unitary algebra. So if I, taking the commutators of these generators, I obtain the whole algebra, then I know that the system is controllable. So I can implement any unitary operator. But the problem with infinite dimension is the unitary group in infinite dimension is not compact anymore. And not only that, even if you restrict to Gaussian operations, so to the symplectic group, this is not compact. So we wanted to understand why. And so if you read the papers about controllability in infinite dimension, you always find that you can't apply the algebra rank criterion. We wanted to understand why compactness is so relevant for controllability. And if you go through the proof of the rank criterion, you find that basically controllability is used in terms of dynamical recurrence. So basically, you want that your generators are not only described, generate the whole algebra, but also they recur. So after some time, they go back to the identity. So this is not true in general for non-compact compact groups. But then if you look at harmonic oscillator, your observation, your experimental observation is that they do recur. So you have spring, you see that it comes back where it started at some point. So this moved us to look if there is a way to go around this problem. And we managed to do that by observing that for quadratic Hamiltonians, dynamical recurrence is obtained for any positive definite Hamiltonian matrix. And this basically led us to a stronger end criterion for quadratic Hamiltonians, saying that if given our generators, our control Hamiltonians and H naught, if we are able to find Hamiltonian H prime, Hj prime, such that they still generate the algebra, they're also positive definite, then the system is quadratically controllable, so Gaussian controllable, which means that we can implement any symplectic operation on the system. So this was in this paper, and I want to stress that any symplectic is maybe not all the group, of course, but not all the unitary group, but it's already a lot, because in practice you can cool your system, you can squeeze it, and you can generate entanglement. Yes?
And did you consider pure state?
No, this is, you don't really...
No,
so
this is not, this is much more. But did you consider for pure state Gaussian state controllability?
Yeah, basically yes, because this is the level of unitary operation. So
yeah, but what I'm saying is that could be a smaller one, like for
okay.
fermions it's smaller, or for spins it's smaller.
Okay, no, we didn't look into state controllability, so we stopped at this level. Okay, thanks. And I have to say that there are other approaches for the control of infinite dimensional system in the literature. You can look at finite dimensional approximations, for example, of this control theorist in Paris, and also Daniel, with one of his PhD students, also generalized this criterion to discrete spectrum Hamiltonians. And anyway, one more thing about this. So I want to give a practical example of this criterion, and this is the case. So you can consider a chain of oscillators that interact by means of this always-on Hamiltonian H naught. So you have free Hamiltonian, then a sort of min-splitter interaction, and also squeeze interaction. And then you consider that you have only these local control Hamiltonians on the fourth side of the chain, which is one is phase rotation and the other one is squeezing. And you can prove that this situation fulfills the strong rank criterion, and then it means that by means of this control, you can implement any symplectic operation in the chain. So if you want to squeeze this one, in principle, by just changing this, switching on and off this control Hamiltonians, you can squeeze this one, or generate entanglement between the second and the fourth, and so on. So this would be, and for example, if you don't have G2, which is the squeezing operation here, you can prove that still you can you generate the compact part of the symplectic group, which means that you can implement phase rotation and min-splitter interaction between all the modes. There are still some open questions, also regarding only just our strong rank criterion. What we proved is just that this criterion is a sufficient condition for controllability. Usually, you have also that is a necessary condition for compact groups. And so we wanted to ask this question, and at least we have the answer for the easiest case for n equal 1 mode. And basically by using this paper where they proved the controllability of SU11, which is isomorphic to SP2, so when you have one mode, then here they proved that the condition is both necessary and sufficient. They use different terminology, but then if you go through the isomorphism between the two groups, you find that their condition they obtain is exactly the positivity of the Hamiltonian matrix we define in our setting. And about the generic number of modes, this is still an open question we would like to work on. Yes?
So, and when you say this, do you mean that you want to say that your Hamiltonian is like, have this positivity criterion, and what is the other criterion to have? Or you can even dump that criterion?
No, we want so what I mean with this strong rank criterion is that you have the usual rank criterion, so you have the whole algebra, and then you want that these generators are also positive definite.
Okay.
And this is sufficient, but we would like to prove that it's also necessary for controllability.
Your guess is that it's true?
This is true for n equal 1, and yeah, our guess is it's true in general, but we still have no proof about that. Yeah. Okay. So now I can move on to the second part of the results. This is about continuous measurement and feedback control, and this is something I've been doing with Alessio and Stefano Mancini from University of Camerino. And so this is the setting we have in mind. We have a finite number of harmonic oscillators interacting with them. We are still considering quadratic Hamiltonians. Every oscillator has its own environment, and the dynamics is described by a Limbach master equation. And as I said before, the evolution is Gaussian. So if we start with a Gaussian state, we still have a Gaussian state, and we can look only to the covariance matrix evolution. And so this is something I've already said before. The evolution for the covariance matrix is described by this equation, and well, this is an example of the drift matrix and the diffusion matrix when you have that every oscillator is interacting with a finite temperature bath. So this is basically the loss, and this is the number of photons of the bath. You can solve the dynamics, you can find the steady state, and so on. But then we want to make a further assumption that we are able to measure the system on time scale, which are much shorter than a typical system response time. So we want to implement this continuous measurement, or what we can call also quantum filtering. There is a lot of work about that. It has been introduced by Belafky, and then there are many ways to look at this problem, and we have seen a lot of talks during this program about this. And I want to stay on the Gaussian world, and this is something that Alessio has shown on the blackboard last week. If you consider the conditional evolution due to this continuous measurement, then you find that your first moment, so for Gaussian state, you look only to the first moment and covariance matrix, and then the evolution of the first moment is stochastic. This means that the first moment changes depending on your measurement outcome, but still you can. The good thing is you can always set them to 0 by using linear Markovian feedback, while the evolution for the covariance matrix is completely deterministic. So no matter what is your outcome of your measurement, the covariance matrix evolution is always the same. You have a closed form equation for the evolution of the covariance matrix depending on the measurement you're implementing. And by looking into this equation, you can find also some conditions that a covariance matrix sigma can be obtained at steady state by performing this continuous measurement. And these are the two conditions that you have to bear in mind. So the second one is just a physicality condition, and the first one is what you exactly have from the equation, deterministic evolution for the covariance matrix. And you can find this, for example, in this paper by Wiseman and Doherty. And the question that one may ask is, okay, how much is the maximum squeezing and entanglement achievable that we may obtain by given a certain quadratic Hamiltonian and a certain Liebman master equation, so given A and D. And this question has been addressed first by Alessio and Stefano Mancini in this PRL, and then has been generalized also in this other paper where we consider, here you have only entanglement and 0 temperature bath. Here we consider also squeezing and the case of finite temperature. And as you can see, and basically what you have to do is just diagonalize these finite dimensional matrices A and D, obtain these your eigenvalues, and then you have these bounds on the squeezing and the entanglement you can achieve by doing continuous measurement and feedback. So our really simple formulas. This is the bound on the negativity of the entanglement. Bear in mind that the smaller is lambda 1, the larger is the squeezing, so that's why you have this kind of bound. So this really means that this is the maximum squeezing you can achieve. I have to say that there is a different approach on basically the Gaussian states you may achieve in open quantum systems, which is not related to continuous measurement feedback, but is more about, I think, reservoir engineering. So you can, and there is this paper by Yamamoto, I think it's been published, but I gave, this is the archive reference. And so I will show you some examples where we can use these bounds. And so let's consider really a simple one. So you have one harmonic oscillator, and you have an interaction Hamiltonian that basically generates squeezing, and then you have a lossy environment. So this is just the Limbat-Master equation corresponding to loss. So you may think that you have a cavity with some nonlinear crystal generates squeezing, and then you have some output that you can measure. And if you don't do any measurement, or if you measure it and you don't look at your measurement outcomes, this is the steady-state squeezing you will obtain. If you use our formula to look at the squeezing, you obtain this bound. And this is the behavior of the two quantities. This is steady-state squeezing without continuous measurement. This is the bound. Of course, this is the threshold. So for larger values of chi, you don't get stability in your system. And the good thing is that it's also easy to write the optimal strategy. So which is the optimal detection you have to implement to obtain this bound, and it's just continuous homodyne detection of the quadrature that is squeezed by this Hamiltonian. So this is a stochastic master equation. If you go through the calculation, you will obtain that the covariance matrix will be squeezed with this value of lambda 1. Now, I would like to go to a more suspicious example. And as I said before, our bounds all also in the case of finite temperature. And let's consider this case, just your oscillator without any interaction Hamiltonian, and then a lossy evolution in internal bath. So this is your master equation. Of course, if you don't do anything, your steady state of the oscillator will be a thermal state with the same temperature of the bath. So no squeezing at all, for sure. But if you look at our bounds, then you obtain this really strange result. So lambda 1 is 1 over 2n plus 1. This means that the larger is the squeezing, you get larger squeezing for larger temperature of the bath. The first time we saw this result, we said, okay, there is something wrong in our bounds. Then we checked it was correct. And not only that, we also managed to write formally a stochastic master equation, which is legitimate. And by using this stochastic master equation, you can achieve this bound. But we couldn't find at the beginning any way, so any physical model for this stochastic master equation. So what we did, okay, let's consider the most general thing we can do. We said is, okay, we have our thermal bath, and we can do a general dyne detection on the output. General dyne detection in general correspond to monitoring this operator for this parameter upsilon, which goes from -1 to 1. And we also prove that you can always implement this measurement by using this scheme. So by mixing your state with a vacuum, and then homodyning X on one output and P on the other output, they commute. And basically, it's well known that for T equal 1 out, so for a 50-50 beam splitter, this implements the heterodyne measurement, so Y upsilon equal to 0. And then we proved that basically by changing this beam splitter reflectivity, transmissivity, that you can basically perform this measurement for any upsilon. And so we did this, and then we derived the most general stochastic master equation corresponding to this monitoring in a thermal bath. There was already this result for homodyne detection, but there were no results for heterodyne and other kind of measurement. And okay, this is the most general result, but then if you look at steady state, you find that no way, you can't get any squeezing steady state, so everything makes sense, because we don't expect you can get that squeezing for free by just looking at some incoherent path here. And so, okay, we are still missing something. And okay, what else we can think of is that, okay, you have an oscillator, and the dynamics is described by having the oscillator interact with a thermal bath, but then you can always think of a thermal bath as a mixed state, which is a partial trace of a larger entangled state. And in particular, if you add another mode here, which has no physical sense, maybe, I don't know. Then the state of the bath is a now two-mode bath with preparing a two-mode squeeze state. And then you assume that you can monitor simultaneously both modes, so you can implement homotime measurement both here and there. Then what you get is exactly our stochastic master equation. So the take-home message is that, one more thing before the take-home message of this part is that you can also consider partial purification of the bath. So if you consider a noise evolution for these two-mode squeeze states such that anyway the master equation you obtain is always this one, there is a nice way to do that such that you can use this free parameter gamma is for gamma equal to 0, you have a two-mode uncorrelated thermal state. So, and for gamma equal to 1, you have the pure two-mode squeeze state here. Then you can derive the general stochastic master equation corresponding to this situation, and this is the steady state value of your variance of the quadrature x, and then you can see that this goes from the thermal state variance for gamma equal to 0, so 2n plus 1. If you put gamma equal to 1, you exactly obtain 1 over 2n plus 1. So, and then you have continuous values between one and the other. And so before going to this, the take-home message is that if you use the formalism introduced in that paper by Wiseman and Doherty, when you have a finite temperature bath, so with a mixed state, you have to be careful in using those bounds and also using those conditions on which covariance matrix you may get given that dynamics. And so that's why also with Alessio, we try to rephrase all those stochastic master equation in terms of the real measurement and the bath state, and so that you can probably go around these problems and maybe find also some more physically reasonable bath when you have finite temperature. I have to say that you don't have this problem with when your bath is in the vacuum state, so in zero temperature bath. Okay, so let's move to the last part, which is a little bit different. And this is about something I've been doing the last year in collaboration with Matteo Bina and Stefano Olivares from University of Milan and Gabriele Chiara and Mauro Paternoster from Queen's University Belfast. And what we are considering is a hybrid mechanical system. What we mean is when you have a quantum mechanical oscillator which is coupled to a two-level system, so to a qubit. And there is a nice review about this system on the archive. Probably will be also a chapter in one book someday. And the good thing about this system is that maybe in the future oscillator can be used as a sensitive probe and readout device for the properties of the qubit. But more likely nowadays you can think to use the qubit to prepare and detect non-classical states of motion, because at least at this stage it's usually we have much more control on qubits than on mechanical systems. You have different examples of this mechanical system, hybrid mechanical system. One of them is this nanomechanical oscillator with a magnetic tip, which interacts with the NV center in diamond through a magnetic field. Or you have also some superconducting circuit where you have a resonator with a superconducting qubit, which is a Cooper pair box in this case. Or you have also the standard case of quantum automechanics. So you have a cavity. One of the two mirrors is a moving mirror, so you zero oscillator, and then you put an atom inside the cavity. In some limit, for example, the bad cavity limit, you can adiabatically eliminate the cavity field, and you obtain an effective interaction between the atom and the mirror. And the good thing is that in all these cases, the Hamiltonian is basically the same. So of course you have the free Hamiltonian, but in particular the interaction part is sigma x times A plus A dagger. And also in all this case is quite easy for the experimentalist to prepare the state of the qubit and read it out accurately. So let's focus on this quite general Hamiltonian, and let's consider for the beginning this parameters regime. So a large detuning between omega A, which is the frequency of the qubit, and omega n. We consider omega n much larger than omega n. Because of this regime, basically you don't have transition anymore on the qubit. You can adiabatically eliminate it. And you can theoretically derive an effective Hamiltonian describing the system. There are many ways to do that. And I particularly like this paper by Gamil and Daniel James on Physical Review A to find this kind of Hamiltonians. And if you go through their formulas, you obtain this new Hamiltonian with this interaction part, where now sigma x a plus a dagger is replaced by sigma z a plus a dagger squared, with a new coupling constant, which is g squared over omega a. And okay, now let's focus on this new effective Hamiltonian. As we said before, basically the qubit is adiabatically eliminated. It means that is decoupled. If we prepare it in an eigenstate of sigma z, is decoupled from the oscillator. And so we can replace it with an effective Hamiltonian only for the our mechanical oscillator. And the nice thing is that this term is a term that can produce squeezing, in particular of the quadrature a plus a dagger. And in particular, we want to obtain squeezing a steady state, so we consider also some decoherence, and in particular, we consider just pure loss, so the usual Limbaugh-Master equation. And in particular, this is the main source of noise in this case, when this is basically the loss that you have in heritage from the cavity field here. Of course, we can also include the temperature here, and I mean, if you ask, I may later discuss what happens if you put temperature, but let's focus on this from now on. And if we consider the effective Hamiltonian and this Limbaugh-Master equation, then the dynamics is can be analytically solved for Gaussian states. We discussed this before. And in particular, you can obtain the analytic formula for the variance of the quadrature x steady state, which is 1 minus something that is always positive for any non-zero value of the coupling constant g. So this is a good, nice result, but then we want to understand, okay, this is what we get with effective Hamiltonian. Is the effective Hamiltonian really describing our system also when the detuning is not so large? And what we plotted here is the evolution of the variance of delta x. And the green line is the exact evolution you obtain numerically with ab initio simulation with the initial Hamiltonian H1, so the original one. And the dashed blue line is the effective evolution you can obtain analytically with our effective Hamiltonian. And with these values of your parameters, so with a really large detuning, you observe a perfect match between the two curves. If you decrease omega a, you start to see something not going exactly where you wanted. And if you decrease again, in particular, let's focus on these values of parameters. After some time, you also lose all the squeezing in your oscillator. This is in dB scale, so values of delta x in dB smaller than 0 correspond to squeezing. So this is quite a sort of a bad news. We may expect that because that was just an effective evolution. But the bad news is also that the squeezing you get when you have larger tuning is not that much because of this omega a under the denominator. And so it would be nice to obtain the same amount of squeezing also in the not so large detuning regime. And we wanted to understand why the effective evolution the effective Hamiltonian doesn't work anymore. And one of the reasons is that basically you start to have transition in the qubit state, and this will lead to squeezing in orthogonal direction during the evolution. Then you trace out and you end up in a big thermal state without any squeezing. And so our idea is, can we try to implement any feedback loop able to force the oscillator to follow the adiabatic dynamics we have seen before? And so we talked about this and we came up with this protocol. So it's quite simple. So you start with your initial state at time t0. You let it evolve for a finite time delta t with your evolution, so with your h1 and then your Limbaugh operator. And after a time delta t, you measure the qubit. Anytime you find it that is not in the excited state, you do a conditional operation to send it back to the excited state. So every time you find ground, you send it back to the excited state. And on average, after a time t1 equal to t0 plus delta t, you find this average state. I mean, you can go through the formula, but it's basically everything is described here. And you repeat this procedure until the harmonic oscillator reaches a steady state. And as you can see, in all the protocol, the only free parameter is basically this finite time delta t. And there is a trade-off here, because in the way I explain why we want to implement this protocol, you want it small because you want the qubit to stay always in the excited state. But if you remember our effective Hamiltonian that is able to produce squeezing, the squeezing is a second-order effect. So you need to wait some time to build up any squeezing in your oscillator. And in fact, if you implement our protocol for different values of delta t, you obtain really different behaviors. And in particular, if you only plot the steady state values as a function of the delta t of your protocol, you obtain this really nice oscillating behavior, where you can see that basically the optimal choices correspond to multiples of 2 pi over omega a. So where omega a is the frequency of your qubit. And in particular, the best one is when you have delta t equal to pi over omega a. So this is the optimal value. This has been done for different values of different regime, and you always obtain this kind of oscillating behavior. So you consider this value from now on, and this is basically our main result. As you may remember, this is the green line is what you get without any feedback by doing the exact evolution with your initial Hamiltonian. The dashed blue line is the effective evolution that doesn't hold anymore in this regime, and the purple line is what you get by using our feedback protocol. So of course it's not exactly the same evolution, but you can see that you are able to recreate that sort of dynamics, and in particular you find a reasonable similar value of squeezing at steady state. We also consider the case of an initial thermostate for your oscillator, and again, maybe you don't have exactly the same oscillations of the blue line, but on average you obtain the same behavior and this similar value of squeezing at steady state. And yeah, I think that's basically it. These are the conclusions. I hope that I've convinced you that controlling continuous variables is something interesting. In particular, I've shown you how to generalize some controllability criterion for open loop controllability to quadratic Hamiltonian, so to Gaussian operations. And then I moved to continuous measurement feedback control, and the take-home message here, as I said, there are these nice bounds on squeezing and entanglement. You have to be careful when you have a finite temperature bath using these bounds, and the formalism in general derived in these cases. And then I moved to this hybrid mechanical systems, and I've shown how to use a different kind of feedback protocol able to reproduce some adiabatic dynamics and to obtain squeezing a steady state. And I think that's it. Thank you for the attention.
Okay, thanks. We've got a bit of time for questions.
Just one comment on controllability and observability. I think it's worth looking into the historical motivations for controllability and observability. So they arose, I guess, in Coleman's work on LTG control, I guess, many, many years ago, 1960 or thereabouts, 1931. And so controllability and observability arose in study of optimization problems. And these algebraic conditions came out naturally by looking at the well-posedness of those optimization problems. And then, of course, the physical interpretation in terms of steering states and things like that came afterwards.
You're referring to closed loop controllability, no?
Yeah, I talk about the classical theory of controllability and observability. And so that was all at the level of what you might call the phase space, right? The X's and the P's,
yeah.
Right? And so it was never considered to be looking at the controllability properties of the corresponding probability distributions. And so I guess my feeling is it's fairly important to focus on the right questions for controlling observability. And so it may not be useful, like, even to consider the controlling observability at the level of the states for Gaussian problems when you
Yeah, because what I understood before, for example, in the previous talk, is that when you talk about controllability and the state, you can, probably is also your comment before to the question by Alessio, that you, when you talk about controllability, sometimes you refer only to the average of XMP in some sense.
The optimization problems from LPG are expressed in terms of optimizing a criterion which is expressed in terms of mean values and covariances. And for Gaussian states, that's all you need, right? And so if you then start to
but you have also the same, so everything is also done also in terms of variances of covariance matrix you get for your probability distribution.
Well,
because
I guess
this
really,
is
the mathematical point really is that there are different levels at which you can consider control of observability. You can do it at the level of the states,
Yeah.
you can do it at the level of phase space. And what's special about linear Gaussian systems is that the states are characterized by finite parameters.
Yeah.
And that's much more easily done using the rank conditions that Coleman gives. And so I find myself struggling to see the motivation for some of these more abstract aspects of controllability for the Gaussian linear problem. So it may be relevant for non-linear problems.
so one thing is I'm not sure if you're talking about the first part. Yeah.
Sorry. No,
Go. No, really. Oh, please. Okay.
I am interacting virtually, so go.
I'm not sure. Are you also talking about the first part, so this open loop controllability, or? Yeah. Okay, but if I understood well, when you talk about Kalman filter and so on, then you also consider maybe there are rank conditions also there, but then you are talking about something different. So you're talking that you're measuring your system and then where you steer your state by doing this measurement. This is just open loop, so you have no measurement at all, and this is not linear. We found results on controllability, but for linear Hamiltonians and while here is also when you implement also squeezing operation and stuff like that. I don't know if you want to add something about this.
I think it's a comment on the comment in a sense. Regardless of the state, it's still interesting to know under what conditions you can do any symplectics.
Yeah.
Just mathematically, right? So if you find a sufficient condition such that you can control any, still interesting.
Yes, but I'm saying that if the scope of your class of systems that you're considering are linear systems, quadratic Hamiltonians with Gaussian states, and that has a finite dimensional parameterization, so you just need to work in that finite dimensional.
No, but
Yeah,
if you can do any symplectic, you can apply it to any state.
Yeah.
Regardless of the parameterization of your state.
So as far as I know, people haven't really looked at problems of controlling observability for the classical analog of what you're doing, I guess, is what I'm trying to see. Because in a sense,
controlling the covariance matrix.
yeah, you're doing it.
Well, then you're talking to the second part.
Yeah.
Then you're talking about this part, not about this. Yeah, but then you have you have something quantum here, also in the bounds that we have derived. You have to impose also the condition of the quantumness of the covariance matrix. So you have different results on what you can get in general, given the same differential equation for your covariance matrix. Then if you impose also the Schrodinger-Robertson inequality, then you have different results from that. So it's not, because for classically you just ask that sigma is positive and that's it.
There's no question about those issues. I mean, certainly it's clear that quantum systems will have special conditions on the ABC. We've already seen them in the physical realizability. That still holds true. All I'm saying is that if you are dealing with problems with finite dimensional parameterization of the states, then the natural place to answer questions of control variability is through those parameterizations, and not through an abstract interdimensional theory, which is more relevant for nonlinear systems.
Well, I think it's also a matter of taste what you call abstract in general, because for me it's not abstract.
I think it would be really worthwhile going back and looking at some of Kalman's early treatises.
Yeah.
Because it did arise from optimization.
Yeah, I agree that basically these two custom master equations, you can always see them as just sort of Kalman filters, but then there are some, as I said before, you have also condition on the quantumness of your covariance matrices. So if you look where you're going, so which is something that you don't have classically.
No, but that's
Yeah.
that's a true statement, and there's nothing I'm saying that's disputing
Okay,
that.
yeah.
But I'm just saying
Yeah,
that
yeah.
I think it would help your investigation.
But I think it's just a matter of taste because you're more used to the camera filters and it looks more familiar. To me, it's not abstract, this formalism in some sense, no?
No, but I think if you're trying to understand more thoroughly questions of observability and controllability for quantum systems, it would be very helpful for you to look at some of Kalman's early work.
I think, well, that's true.
Yeah, that's true.
That's my main
No,
comment.
yeah.
And then I think also it's important to address the questions in the right level of generality.
Yeah.
To the problem you have at hand.
And another thing, I mean, it's not, when you talk about controllability, there's no open loop or closed loop. Controllability is controllability, how much
Yeah, I agree.
control authority you have by certain.
But it's a different problem, no?
Whether
You're
you know
defining the
what
rules
you're
of your
doing
game
or
before.
not is a different story to close the loop.
Yeah.
But the control authority is sort of the one channel.
Yeah, I kind of agree. Yeah.
I guess there was some work on control of covariance matrices. Classic, I think, was by Bob Skelton did something. So there is some work out there. I'm not quite sure the relevance there.
So I think actually that problem goes back to the Schrodinger bridge problem that we
Exactly.
talked about the other night, where
Yeah.
we're also talking about controlling classical probability distributions.
Exactly.
And so
No,
if
this
you
is-
restrict to the linear
Yeah.
Gaussian caps, then the probability distribution is essentially just determined by the covariance matrix. And so there is that sort of classical problem.
Yes, Schrodinger bridges is exactly that.
In fact, like for instance, in this case, with some of the bounds, like one thing that probably wasn't highlighted properly is the fact that those like detectability, we bypass it because we just consider stable systems. They are already naturally
Yeah.
stable.
Yeah.
So
Yeah, you can
then
see
so
basically.
implicitly the drift
Yeah,
matrix is negative definite somehow, and then so for instance, so we did consider that. So we should look into, for instance, unstable systems.
System, and you
then
can,
classical
yeah,
detectability
do the
conditions
software.
are certainly very relevant. That's true.
Yeah, so I think it's beneficial to understand
Yeah.
thoroughly the classical literature as well, in this area in particular. So it has a very long history, going back 50 years.
But I mean, again, though, this optimization was never done classically.
Yeah.
The EN, that's
For
another
sure.
point. Because that's something that that's the something on the symplectic eigenvalue on a matrix,
Right.
which is of a transposed or partially transposed matrix of a composite system, and that classically doesn't have any relevance.
So for sure
It's just a
yeah.
quantifier of entanglement.
Right.
So-
So yeah, the second equation is.
And
So the first
quantum.
one certainly, yes, is classical.
So you have the second equation, which is fully quantum, and in particular, you can talk about entanglement only.
So the second equation is kind of like the Heisenberg uncertainty principle,
Yeah.
really. And
Yes,
so
yeah.
you've just got the normal covariance matrix Lyapunov condition, the first one, and then you pose the Heisenberg's uncertainty principle, and then it becomes a quantum problem.
Yeah, so it's clearly important to be focusing on what's special about the quantum systems
Yeah.
when you're studying quantum systems. But I think a lot of useful insights can be gained
From classical, yeah.
Well, of course, those results won't be available, but a lot of historical context and even some useful results will actually be very useful.
Yeah, I agree on that.
That's
I have a just related question, but about the last word about hybrids.
Mhm.
So how do you physically understand the kind of Hamiltonian? You have the J's coming from Hamiltonian because usually I'm used to when you talk about non-mechanical resonances, I'm used rather to see in terms of form A dagger A and sigma X.
So this Hamiltonian.
Yeah. How do you understand this physically?
Well, this is also when you have James Cummings, basically you start from that, and then since
Yeah.
you have
but I don't. I mean.
the second one, you
No, but how do you get? What does this physically? How do you understand this? What is happening that you have such kind of? What's the kind of coupling there? So you have this atom which is coupled to what? I do not understand this physically.
here you have basically the usual optomechanical Hamiltonian between. You mean in this
So
case
you
is
have
really
actually you have already eliminated.
Yeah.
some of the
In these
actual-
cases, this is the real. I mean, under some assumption, is the Hamiltonian you get from the interaction between your oscillator and your qubit.
No, but
Yeah,
you have
in
another
that-
oscillator that you have.
Yeah, in
before.
that case, you already limited the cavity field.
The cavity.
Yeah.
Okay, which gives you that.
Yeah.
And so then, in order to get the effective Hamiltonian, you assume that your resonator's frequency is much smaller than this coupling G.
No, of omega A.
Omega, yeah, I'm sorry. The
Of-
qubit's frequency is much smaller than.
No, the qubit frequency is much larger than the oscillator frequency, which is something that you.
But how does this compare to G?
G, to get something, I mean, as you can see from the examples, I mean, so, okay, let's go to this is an example where also the feedback protocol works.
Yeah, so it's
Then,
smaller
yeah.
than G as well.
G is smaller than omega A, right? And the problem here that we are not yet probably at this level in experimental, from the experimental point of view, is that G is not 10 times omega M right now. So
that's what I'm saying. Yeah. So you assume that G is because if you go back and it seems to me that your effective coupling lambda is G squared over omega n. That's what you say.
Yeah.
So that's I feeling like omega A. Okay.
Omega A. Yeah, this is the detuning also. Usually, when you have this kind of effective Hamiltonian, you have the detuning, but since this omega A is much larger than omega n.
Usual dispersive kind of
Yeah.
expect that you have okay, so it's omega A minus omega B.
Yeah.
Right, if there's no further speakers, let's stop. Thank Marco and
Maybe it's more like